Hey everyone, and welcome to The Explainer. Today, we're taking on something that honestly leaves a lot of students and even seasoned pros scratching their heads: ordinary differential equations. But look, we're not just going to sit here and crunch numbers. We are going to visualize this math. I want you to look at these equations not as, just abstract symbols on a page, but as an actual blueprint for a mechanical architecture. We're going to build ourselves a mathematical engine, piece by piece, to really demystify how these systems actually work. Okay, let's dive right into this.
Here's our 6-part blueprint for the machinery we're about to build. We've got anatomy of a system, rules and diagnostic tests, the core eigenvalue engine, real eigenvalues in action, the complex complication, and finally, the Euler bridge to reality.
Section 1. Anatomy of a system. The blueprint.
So, before we can rev up our engine and start solving things, we absolutely have to understand the basic parts of the system we're dealing with, right? Our foundational equation here is a first-order linear system. That's x prime of t equals a of t times x of t plus f of t. Now, that state vector, x of t, that represents the variables we actually want to solve for. Think of that as our destination. Then we've got the system matrix, a of t. And I like to think of this matrix as the internal rules running our system, basically the gears inside our machine. And finally, sitting on the end there, we have the forcing vector, f of t. These are the external influences that are being applied to our system over time.
And that forcing vector actually leads us right into a really vital distinction: homogeneous versus non-homogeneous systems. See, a homogeneous system relies completely on its own internal dynamics. It runs in isolation, meaning that external forcing vector, f of t, is just zero. Conversely, a non-homogeneous system includes independent external forces, stuff like a sine wave or an exponential function, that are actively pushing or pulling on our system from the outside.
Section 2. Rules and diagnostic tests. Checking the wiring.
Okay, now that we know the parts, we need to understand the rules governing them. And honestly, we need a way to run some diagnostics before we put together our final solution. Now, the absolute most critical rule in linear systems is the principle of superposition. Simply put, if you have multiple valid solutions running on an interval, well, any linear combination of them is also a valid solution. Imagine you've got 3 separate wave solutions. Through a constant multiplier mechanism, those C1, C2, and C3 constants, you can actually blend these individual waves together to form one grand, structurally sound combined solution, x of t. Pretty cool, right?
Now, what's really interesting here is how we build that grand combined solution. We use a specific diagnostic tool called the Wronskian. Basically, we have to prove that our individual vector solutions are linearly independent. They can't just be copies of each other, right? So we plug our solutions into this Wronskian determinant. If the determinant, w of t, does not equal 0, boom, our solutions are independent. The diagnostic test passes, and we have a valid fundamental set. But if it equals 0, well, the system is essentially short-circuiting, and we got to go back to the drawing board.
Section 3. The core eigenvalue engine, powering the math.
All right, we've checked the parts, we've learned the rules. Now let's meet the absolute star of the show, the actual engine that solves these equations. Normally, if you multiply a matrix A by a specific vector v, it knocks that vector completely off its original path. But for a very special set of vectors, which we call eigenvectors, multiplying them by matrix A simply stretches or shrinks them. It doesn't rotate them at all. And that linear stretch factor, that's our eigenvalue, lambda. So A times v equals lambda times v. The eigenvector gives us our fixed direction, and the eigenvalue dictates exactly how intensely we're moving in that direction.
So how do we actually find these magical vectors and values? We use a super clean 3-step operational framework. Step 1, we use the characteristic equation, that's the determinant of a minus lambda I, set to 0, to find our roots, which are our eigenvalues. Step 2, we take those eigenvalues and plug them into the homogeneous system so we can solve for the corresponding non-zero eigenvectors. And step 3, we assemble all those pieces right into our general solution.
And I gotta say, the resulting general solution is incredibly elegant. Look at it. The eigenvalue v dictates the spatial direction of our system. Meanwhile, the eigenvalue lambda sits right up there in the exponent, acting as this time-dependent scaling mechanism. It's the engine that determines whether our system is going to experience exponential growth or exponential decay along that specific path.
Section 4. Real eigenvalues in action. The test drive.
Okay, it's time to shift gears. We've got our engine built. Just think about it for a second. We've talked about matrices, vectors, determinants, linear independence, the whole shebang. But how does this mathematical machinery actually look in practice when we,
turn the key and let it run.
Well, in practice, it operates like a beautifully streamlined process. Starting with a 2x2 input matrix, we follow step 1 and find our characteristic roots. In this specific case, our engine easily outputs two distinct real roots, lambda equals 2 and lambda equals -5. Following step 2, we find our specific eigenvectors for each of those roots. And finally, step 3, we cleanly output our general solution. Notice how our real roots, the 2 and the -5, sit perfectly right there in the exponents, dictating the time-dependent behavior of our vectors. The machine literally runs flawlessly.
Section 5. The complex complication, a system breakdown. But what happens when things don't go perfectly? Let's introduce a little plot twist here. What happens when our mathematical machine spits out something that theoretically shouldn't even exist in our physical reality? Consider this stark truth for a moment. Complex solutions cannot be directly interpreted in real-world physical systems. That is our primary conflict right there. Sometimes our perfectly valid real coefficient matrices produce complex eigenvalues, numbers that have imaginary parts. And well, if you're an engineer trying to model the physical swaying of a suspension bridge, an imaginary number really doesn't help you much, does it?
So the crucial point is that a system can fail us, practically, even if the math totally holds up. If an input matrix yields a complex eigenvalue, like say 5 ± 3i, and we plug that into our exponential solution format, it's algebraically correct. The math completely works out on paper. But practically, it is entirely unusable. We absolutely cannot have an imaginary number sitting in the exponential of a physical system state vector. The system is essentially broken at this point.
Section 6. Euler bridge to reality, the ultimate fix.
So, we've got a broken system. We need a patch. We need a way to translate this unusable imaginary mathematics back into the physical reality that we actually live in. Enter Euler's identity. Honestly, this is genuinely one of the most magnificent mathematical patches ever discovered. Euler's formula states that e to the power of I times theta equals the cosine of theta plus I times the sine of theta. This isn't just some random equation. It is a translation device. It literally allows us to convert complex exponents into standard trigonometric functions. Think of Euler's formula as the ultimate mathematical translator. It takes an imaginary unit circle and literally maps it out into real, oscillating sine and cosine waves. This allows our broken, practically unusable complex exponent to be completely transformed. The real part, that 5, becomes an amplitude scalar, e to the 5t, which dictates our growth. And the imaginary part, the 3i, is run through Euler's formula to become our oscillator, cosine 3t and sine 3t. Boom! We have successfully extracted real-world, oscillating physical forces straight out of an imaginary mathematical structure.
Which leaves us with a rather profound question to end on. How is it that abstract, imaginary mathematical structures can flawlessly dictate the oscillating physical forces of our universe? We started with the basic definitions of state vectors and matrices. We built an engine to find hidden geometric stretch factors. We ran into a massive imaginary roadblock. And then we used a trigonometric bridge to find real-world waves. I really hope this explainer helped you visualize not just the how, but the actual why behind linear systems. Keep exploring, keep questioning, and I will see you next time.